Okay, in this lecture we are going to talk about the connection. And we were introduced to the connection in our last lecture when we talked a little bit about the Einstein equivalence principle and geodesics. And we're going to now focus this time on the connection. Now, what did we do last time? Well, last time we assumed that we had an inertial coordinate system. And we've been drawing this picture of a guy sort of in a free-falling lab. But imagine that he's just in a lab moving in the space-time of special relativity. So the whole space-time, everything is all special relativity, which ultimately means there's no gravity and space-time is flat, and it means that the metric can always be written in this form, everywhere in space-time. It means at every point in space-time, this is the value of the metric. It's completely constant, and it's the same everywhere. Now, what is important, though, is that the metric is in this form if you're dealing with what amounts to a Cartesian coordinate system in space, x, y, z in space, and then a simple time coordinate bound together by the fact that the interval of proper time is minus dt squared plus dx squared plus dy squared plus dz squared, right? If you've got to have this kind of coordinate system to have this kind of proper time element to give you that specific metric. But this coordinate system is arbitrary, right? We could do special relativity in special relativity's flat space-time, but without this coordinate system, we could use a polar coordinate system. We could use a cylindrical coordinate system. And that wouldn't change the fact that space is flat just because we're sort of laying out the coordinates in a different way. And if you did that, this metric would be different. It would be different, but it would still, and it may not even be, not only would it be different, but it may not be the same at every point, right? In this case, it is this number, minus 1, 1, 1, 1, at every single point in space-time. But if you change the spherical coordinates, and we'll see later when we do this example in this lesson, that this metric is actually now a function of space-time. And yet, the space is still entirely flat. So from this idea, we're going to create the notion of a connection in completely flat space-time, and then we'll invoke the Einstein equivalence principle, the EEQP, I guess I want to call it the EEP, is what I've been calling it. Then we'll invoke the Einstein equivalence principle to talk about how this might be a good theory of gravity. But going back to just the connection as it is, let's consider that we are using these C coordinates, and I'll use the letter A for those coordinates. And these coordinates are going to be your straight up Cartesian spatial system with the Lorentzian time element. So it's going to be your basic Minkowski coordinate system. And then there's an alternate coordinate system, which we'll call X, and it should be any Greek index. So just for the sake of not colliding with other indexes, I like to use mu, nu, alpha, beta, gamma, delta. Those are the ones I go to right away. So I'm going to put in a theta there just to get a little variety. But in this coordinate system, this could be, say, spherical coordinates. So if it was spherical coordinates in Minkowski system, x0 would still be sort of the time coordinate, but x1 might be the radial coordinate, x2 might be the, I think usually the theta coordinate comes second in spherical coordinates, and usually I think the third is usually the azimuthal coordinate. What is this called? The longitudinal coordinate? I can't remember what this one's called. This is the azimuthal coordinate, represents the azimuth, as it were, for spherical coordinates. So this might be your spherical coordinate system, but this is just going to be your regular time x, y, z system, right? So those are the two systems. So I'm not going to fix this as the spherical coordinate system. I'll do that as an example later. But it could be any system, for example, the spherical coordinate system, right? So, but for it to be of any system of any use, right, for it to be a system of any use at all, it has to be the case that I can write the coordinates in one system in terms of the coordinates in another. So I know that I have these kind of expressions, right? I have an expression that'll tell me the A coordinate in the Minkowski space if I know all of the coordinates in the alternative system, right? 0, x1, x2, and x3. I like to write this out every now and then to remind you guys that this here is not true. Is not meant to be true for just one value of theta. It's meant to represent literally by definition. So because it's by definition, I'll put in 3 lines here. It's literally meant to represent by definition this for all 3 values. And this alpha here, likewise, in that case, I do pick 1. So I am thinking of the 0th coordinate is a function of all the space-time coordinates in the other system. And of course, likewise, we have the same situation going backwards, right? I can figure out any individual coordinate of a point if I know all the coordinates of the point in the Minkowski system, right? So it is important to keep, I mean, I go through this a lot, and that's sort of my thing, right? My thing in these lectures is to kind of beat dead horses. So when you go to real books and you study from people who really know what they're talking about, the notation doesn't intimidate you, right? You see this, you think this, and you just got to kind of know that that's the case. I know I probably said this a million times. I know I said it last time. But redundancy, I don't feel obligated to evade redundancy. It's just the way I think, the way I do it. I've forgotten this stuff more times than I've learned it. Well, no, I guess that's impossible. I've forgotten it one more time than I've learned it, right? Or well, that's not true either. I guess each time I learn it, I forget it, relearn it, forget it, relearn it, forget it. So I guess there's a one-to-one correspondence. It might be the case that I've learned it one more time than I've forgotten it, but that just means I haven't forgotten it yet. So I go through this myself over and over again. Okay, anyway, but then what we said was, all right, so now we have an inertial, an object that is moving in a straight line in the space-time of special relativity. It's an inertial, and we are in an inertial coordinate system, which means that our coordinate system, epsilon A, is inertial. Now, last time when we looked at this, I said because of the Einstein equivalence principle, right? Because the Einstein equivalence principle, we know that a coordinate system exists in the special space-time of general relativity. We know that such a coordinate system exists at a given point. In fact, it's a little better than that. It's usually along a line, but maybe we'll talk about that a little more when we talk about geodesics. But we definitely know that at any given point, we can find this coordinate system. Now, right now, we're not going to do that. We're going to say, okay, we're going to say the whole thing is special relativity. So we don't even have to look for a coordinate system that satisfies, we don't need the equivalence principle because we're not dealing with anything that's free falling. We're dealing with things that are just moving uniform velocities entirely inertially in the space-time of special relativity. And this coordinate system has it. And we know that this coordinate system is rectilinear Minkowski. So it's got eta, alpha, beta as its metric. And I don't even really need to write the metric as a function of space-time. It is, but it's a constant function, and it's always -1, 1, 1. Okay, so that's what we're dealing with here. But now we have this alternative coordinate system, x, mu, and we know both of these functions. We know x mu is a function of the inertial system, and we know the inertial system as a function of x mu. And because we are dealing with an object that's just moving under no forces, in this coordinate system, I will now write down the path of that object. And the path of that object I'm going to call EA of tau, where tau is the proper time. Tau is the proper time of that particle moving in this inertial coordinate system. And I know, because it's inertial motion and there are no forces applied, I know that d, the second derivative of that path with respect to its proper time is going to be 0. It's not accelerating. That's another way of saying that in this coordinate system, this object is not accelerating in any way. It's just moving along on its steady path. Now this whole equation, remember, d e alpha of tau d tau squared. So here we're leaving out the fact that we don't, they very frequently in general relativity textbooks don't include this key variable in these kind of expressions, but this is what they mean. That's a tau right there, right? And so that, again, it can get confusing pretty fast if you're not on top of it. So we know that this is the case. So now what did we do? We just took these derivatives. So we took the first derivative of, we took both derivatives. We took the first derivative with respect to tau and then the second derivative with respect to tau. Let's quickly run through that again. The first derivative with respect to tau was d e a d tau. It's going to be d psi, not e, psi a x mu dx mu d tau. Very easy. Then we do it again. We take the second derivative. So d tau of d psi a d tau equals, and now again we're still exploiting this relationship here, or more specifically this relationship here. That's exploited right here, right? This chain rule, right? This is now being considered as a function of x mu, and x mu is being considered as a function of tau. I guess I should make that clear, right? Here we're using EA of x mu, and we're using x mu of tau. And in this other coordinate system, this is the path of the particle in this other coordinate system. And you can see the problem, right? You know, if we have a particle that's moving this way in the rectilinear coordinate system, then in the spherical coordinate system, its motion is relatively complicated because it's got an ever-changing value of the azimuthal coordinate and the radial coordinate. They're both changing. Whereas in this case, the only coordinate that's changing in the Minkowski system is simply, say, the x2 coordinate, I guess. So, but it's the same motion, right? So the same motion is expressed in the Minkowski system and then expressed in this alternative system, which I've suggested to be the spherical system in this case. So we take the second derivative, right? And so now the second derivative of this thing is going to be d squared EA dx nu dx mu dx mu d tau, and then I need dx nu d tau, right? So it's again, it's just the chain rule their time on the nu case. But this derivative we know because this derivative where the path of the particle in the new coordinate system, that's going to turn out to be the sort of the unknown function, right? That's what we're looking for. We know the path in this system satisfies this law, right? We're curious, what law does it satisfy in this system? And this represents that path. So we know that whatever the second derivative is, we're seeing first derivatives of this function, which may or may not be known to us. It's probably not known to us. But that's only the derivative of this first part. We need to then, so this here it's the product rule, right? It's the product rule. So the next step is plus, it's plus dEA dx mu dx mu dx mu squared d squared x mu d tau squared, right? So that's the second derivative of this thing. But it is the second derivative of this thing, so I can set this equal to 0, right? So this expression now equals 0. And so then the next step was just a little sort of a mathematical, touch of a mathematical gimmick, but we kind of insert a delta function here. We insert, what do we insert? We insert a delta b a, and then we switch this from a to b, right? You got to agree that's not a change. I've got this delta function here that forces a to equal b, and then I take that a and I turn it to b. There's really nothing going on there. But it does allow us to exploit this little fact that delta b a is going to be d e epsilon, hold on, b dx gamma dx gamma d epsilon a, like that, right? Oops, not like that's not the way I want it. I want it the other way. I want this b and this a switched. So it's a little bit, I want that a up there and that b down there. And then if I make this substitution here, right, I put that right up front, then you'll notice I have a d ca dx mu and a d ca dx gamma, but here this is a dummy index, right? This gamma, that's a dummy index. So I can turn it into mu arbitrarily and pull it out. Actually, the way I should do it is I should turn this into gamma arbitrarily. Let me do that. Turn that into gamma arbitrarily and pull it out. And what do I end up with? I end up with pulling out, I get d ca dx gamma times, and then this is left behind, dx gamma dcb, and then it's d squared cb dx nu dx mu, and then it's times dx mu d tau dx nu d tau plus d squared x gamma d tau squared equals 0. Phew. And this, we did this last time, right? We got this far, and this equation, which I am now going to copy and paste onto this part of the board, this equation is our geodesic equation. This equation is what I was calling the geodesic equation. And let's see if I can erase that line. And the idea is that this thing here has to be 0 because this is it was E alpha as a function of x mu. And I said this is arbitrary, right? Right? We're allowed any coordinate change we want. So we can't assume that that's 0, but in order for this to be true, equaling 0, it must be that this expression here equals 0. And that's what gives us our final expression, which is that's not going to ever be 0. That is just messy stuff. That goes away, and this whole thing has to equal 0. So that was our geodesic equation. It's usually written with this first, right? And we should do that because that's the whole point of why I'm reviewing this, d squared x gamma d tau squared plus, and then we created this object, the connection, and the only thing that's gamma, mu, and nu are the only remaining indices, mu, nu, dx mu d tau, dx nu d tau equals 0. This is now a differential equation for x mu of tau, which is the path of this object in, whoops, where did I have that old coordinate system? Hold on. In this other coordinate system, right? So now the this path here was, for example, was E alpha of tau, which was a straight line path in Minkowski space. But now we have x mu of tau, which is the same straight line path, but in the curvilinear space of polar coordinates, right? With r, the azimuthal coordinate phi, and the longitudinal coordinate theta. This is the only one that's constant, right? That's going to be the only one that's constant in this particular path, right? If you had, but an arbitrary path, none of them will be constant. So this is a much more complicated set of expressions than this. But it's still flat space and it's still inertial motion. The point is that when you look at this and you compare the equations of motions in these two coordinate systems, this is the equation of motion in one system, and this is the equation of motion in some arbitrary other system. So in this system, if we think in terms of force equals mass times acceleration, if we just kind of go back to that arbitrary physics, this part is telling us about the acceleration of things, right? This is the acceleration of the body. That acceleration equals 0. So if I multiplied everything by mass here, I'd get mass times acceleration equals 0, so the forces are 0. So here I would get mass times acceleration, right? This is a term here that represents acceleration. But then I also get a mass term here times something else in order to get this 0. So this is mass times acceleration, and then if I move this to the other side, I get mass times acceleration in these odd coordinates equals mass times gamma mu nu, and then what I'll do is I'll call this x mu dot x nu dot, right? So I get the velocities in this new coordinate system times some interesting number, which is the connection, multiplied by mass. So this side has got to be a force because this side is mass times an acceleration. So this is a force. So we have this force that appears just because we're in this arbitrarily new different coordinate system that's not straight up inertial Minkowski space. And that term, right, normally the first exposure to anything like this is the Coriolis effect when we're simply exchanging coordinate systems to the, I think it's the surface of the Earth is the common one, and we start seeing, forces that move things to or away from the equator, depending on how they're spinning and all of that stuff. But this is a force that appears only because we've changed our coordinate system. And that is typically called a fictitious force. Uh-oh. I should know better than to try to spell a word. Fictitious. See, this is why I do math, because I can't spell, and I'm sure anybody of you who's been following this realizes that it's a freaking disaster, my spelling. And my handwriting. And that's not the only things that are a disaster, but those are the only things you guys know. But this is the important part. These fictitious forces appear, and you'll notice this key thing. The force is proportional to the mass. It did not have to be that way. We could imagine a force that was, okay, it did have to be that way. If you believe that F equals ma, there's nothing in our logic. That mass is forced to be in there. But it's a fictitious force and it's proportional to the mass, right? And that is the key observation that makes us think, well, wait a minute, what other force is proportional to the mass? The force of gravity is some constant times the mass of the gravitating body, the body that's the source of the gravitation, times the body that's the subject of the gravitation, divided by the square of the distance between them. So this means that force is proportional to the mass of the body that's subject to the gravitation. Now clearly there's an issue here if you're dealing with two bodies that are subject to each other's gravitation. Interestingly, you can always kind of move to a frame where that sort of goes away, but in the approximation that we have a gravitating mass and a test particle, gravity is a force that is proportional to the mass of the test particle. But you notice how this fictitious force appeared entirely through considerations of nothing but the geometry of how we lay out our meter sticks in space-time and our clocks as well. And this is the central idea that, upon which, in my opinion, general relativity kind of rests. It rests on the idea that gravity is, in fact, an artifact of not simply the coordinate system we choose, but it's an artifact of the fact that the inertial nature of space-time changes under the influence of gravitational forces, and it does so in a very specific way. And these guys here are what drives it, right? Now, in this case, what this is this is simply a bookkeeping tool to keep track of the difference between, say, polar and rectilinear coordinates. Now, what we do is, but in this case, we're also able to say that all of space-time was flat. Everywhere in this coordinate system, we had a metric of -1, 1, 1, and 1. And we make whatever the coordinate transformation is, this new coordinate system has its own metric, which may in fact depend on space-time, or on the position in space and time, but it's still flat, right? And so there is always the question of how do we know when we look at a metric whether or not it's flat? And the answer is, well, can you transform it back into this everywhere? If the metric is everywhere transformable simultaneously to this, you know you have a flat space-time. And another way of saying it is that the Riemann curvature tensor equals, let's see, A, B, C, D. It's a rank 4 tensor expressed in different ways, but it's got to be 0 in every coordinate system. If it's 0 in any, all of the components have to be 0 in well, all the components have to be 0 in any coordinate system, and they will be 0 in every coordinate system because that's what tensors do, right? Tensors, if they're all 0 in one coordinate system, they'll all be 0 in all coordinate systems. So this notion of this fictitious force is really important, and the connection comes up in that context. So maybe we can just whip up a quick example in flat space. So we'll illustrate this in flat space, and we'll use spherical coordinates. Flat space spherical coordinates, and we're actually going to do this in terms of pure geometry, just because it's really just illustrating the process, right? So, meaning when I say pure geometry, we're just going to consider very easy to visualize x, y, z, right hand Euclidean space, and then the spherical coordinates, which we'll use as, we always draw this for it, but we have r and then phi, the azimuthal coordinate, and theta. So we're going to use those two systems, and it's pretty straightforward. The relationship between the two is going to be, now normally I would write x, r, sine theta, cosine phi. based on this set of pictures, right? But what we're really, just to stick with the spirit of the notation of this subject, this I'm going to call E1, not E1, C1, C2, and C3. And this I'm going to call R is going to be X1, theta is going to be X2, and phi is going to be X3, right? So the way this should look is, it should look as C1 equals X1 cosine, sine X2 cosine X3, right? That is the general relativity notation that you would use for this problem that you've probably seen a million times before in electrodynamics. And then psi 2 is X1 sine X2. Now, it's interesting. I should sine X2 and then sine X3, and C3 is X1 cosine X2. And this can be inverted, right? I should be able to write X1 equals X2 equals and X3 equals, right? Now, and also, if I was really hardcore general relativity type notation, I would actually write, for example, this one, I'll put it in green because it's so hardcore, E2 equals E1 prime sine C2 prime sine sine C3 prime, where I'm changing the coordinates by putting a prime in the indices, right? That's actually how I prefer it. And a lot of the really good books would, if they literally were to write this out, they would write it out in that form. So we'll take some sort of intermediate step because we're not going to go much beyond. I mean, this lesson only covers this one subject, so we don't need a notation that's infinitely flexible. So, but we could write these guys here, as I was saying. For example, let's see, psi 1 is R. That's easy. That would be E1 squared plus C2 squared plus C3 squared, all square rooted, right? To the 1/2 power. That would be psi 1. And I guess, since I've gotten this started, psi 3 is easy, right? That's just arctan C2 over C1, right? And C2 I always forget how to do. Let me think about it. C2 always confuses me because if you treat R as the hypotenuse of a triangle, then Z is just the height, right? And so R is x squared plus y squared plus z squared. Z is the height. So the height divided by that hypotenuse would be the sine of this angle, but I want that angle. So I think it's the inverse cosine of C1 squared plus C2 squared plus C3 squared, right? And it's divided by divided by, and then it's C3 divided by that, right? And so, although I wrote arctan here and cosine inverse there, they're both inverse trigonometric functions. So these are E A of x mu, and these are x mu of EA. Now everything is totally flat space-time here. All we're doing is changing the coordinate systems, right? So now once I have that, now I can create the these important functions over here, which, let's go way back here. These guys, right? oops. Let's see if I can find good examples here. We need, which ones are they? We need the derivatives with respect to each other. Well, what we need is we want to calculate gamma alpha beta equals dx gamma partial c sigma partial c sigma dx alpha dx beta. We want to calculate these guys. That's going to be our example, right? So what are we doing in this circumstance? We're taking a coordinate transformation in flat space-time, in the space-time of, well, it's not even the space-time of special relativity right now, right? Because we're not including time. This is just normal Euclidean geometry in 3 dimensions, right? So we've got 3 dimensions of flat space in polar coordinates and in Cartesian coordinates. And these connection coefficients are going to be introduced as a result of this in this coordinate system. Inertial motion in this coordinate system is going to generate these connection coefficients when looked at in this coordinate system. And that basically means that we're going to see things forcing an acceleration in the r direction, right? Because remember, as a particle moves linearly, right? As a particle moves, say, in this direction, r gets smaller and smaller and smaller and smaller, and then bigger and bigger and bigger and bigger, but not at a steady rate. R changes faster right around here, and so it's actually accelerating. The change in r is accelerating, and then the farther it gets away, r tends to just change less and the r accelerates less and less, and appears to have greater and greater similarity to what, say, the y-coordinate would if it was moving in this direction, right? Yeah, and that's a good way to think about it. If the particle is moving parallel to the y-axis and it's not changing in z or x, the y-coordinate is changing at a constant rate for an inertial motion particle, right? Now here, if you go way out here, the r-coordinate is changing similarly to the y-coordinate if you're very, very far away. But when you're right here, you see this weird acceleration in the r-coordinate, right? And that acceleration is driven by a fictitious force that's captured through this connection coefficient, and it's expressed in this expression right here. The acceleration in the r-coordinate with respect to the time of the particle moving it's not zero. It actually depends on the current velocity of that particle, which sort of implies relative to the r coordinate, and these connection coefficients, right? And so if it was in the xyz coordinate, all of these terms would be zero if it was in the Cartesian system, and it would just look like there's no acceleration in the y coordinate, but in the r coordinate there will be. And that's just entirely a product of the coordinate system we choose, entirely a product of that coordinate system. So we want to calculate this, and let's do it for an example. Well, let's look at this. Say gamma, alpha, and beta were all the same thing. Say it was 0 or 1, 1, 1, right? Well, if it's 1, 1, 1, then we need the derivative of x1 with sigma 1, sigma 2, and sigma 3, because this is going to be a sum, right? Maybe I should actually write that out. This will be a sum, partial gamma, partial x gamma, partial c1, partial c1, partial x alpha, partial x beta, plus partial x gamma, partial c2. This is squared here. That's a squared there. Partial c2, partial x alpha, partial x beta, and likewise for number 3, right? So this is we're summing over this dummy index here. So if we just looked at this term, we have partial x gamma, partial c1, right? So that's going to be a derivative of this. So it's going to be 1/2 times this to the negative 1/2 multiplied by 2c1, right? So that's not going to be 0, but c1 alpha beta, if we go here, the derivative of this with respect to c alpha c beta, well, that could get messy. If it was c11, however, if it was c11, then it'd be two derivatives with respect to x1, so that would be 0. And that would be true no matter what. So if alpha and beta are 1 and 1, we know you're going to get 0. So all the forms C this 1, 1 will always be 0. And you can tell that right away because the second partial derivative with respect to 1 for this coordinate transformation is going to be 0. Not true for all of them, and you could work this out. You can actually calculate this for each and every case. I suppose we should do it for one case just for completeness' sake, so why don't we pick one that's not going to be 0? So which one will not be 0? Well, if let's see, I want to find a simple one that's not going to be 0. So let's say this was 2, 2, right? The first derivative of this with respect to x2 is going to be x1 cosine x2 cosine x3, and then the next derivative will be minus x1 sine x2 cosine x3. So that won't be 0, and then so at least one term won't be 0. Now there's always a chance that there'll be some kind of cancellation, but if we looked at gamma, say 2, 2, let's try to calculate gamma 1, 2, 2. I don't think that one will be 0. All right, so this is guaranteed to be a pain in the butt, but let's persist and see if we can make this work. In fact, I'm pretty sure gamma 2, 2, I remember gamma 2, 2 is probably the only, gamma 1, 2, 2 is probably the only one that's not equal to 0 in the spherical system. I'll double check that. I don't exactly remember offhand. But anyway, what do we need to calculate? The first term we need to calculate is partial x1 partial psi 1 partial squared psi 1 partial x2 partial x2, like that. And then we have these other two terms that are similar. So this first one, partial x1 partial psi 1. Now we're going to our, this is the function we have to use, right? This is the dependent variable. This is the independent variable. And just like I said, this really means partial x1 as a function of psi a partial psi 1. Right? So we can take that derivative. There's no doubt. And there's the function that we use for it. Right? So taking that derivative, what do we get? Well, we're going to get minus, no, we're going to get 1/2 of, and then it's everything inside these parentheses, right? But notice, with all the stuff that's inside these parentheses, it's actually, it's r squared, right? Square root of r squared. Interesting. So we get, you'll see that'll simplify things in a moment. So it's e1 squared plus e2 squared plus c3 squared to the minus 1/2 times 2c1. So this will simplify to c1 times, and then this thing here, right, is just 1 over x1. So it's c1 over x1, right? That's what the first term is. So the first term is c1 over x1. That's when I say first term, I mean the first factor, right? We're working on the first term of the sum of this thing, and now we're attacking the first factor of that term. So I think that first factor is this, is c1 over x1. And you know, if you were using the other notation, this would end up being, it would be x over r, right? x over r is what that would actually be in sort of more elementary physics type notation. So then there's that. Now the next term is c1, take two derivatives of x2. So now we're using this function, right? We interpret this statement as the second derivative of c1, which is a function of the x coordinates dx2 partial x2. Now notice this is this is the second derivative up here, but in this case, normally you'd have second derivative of f, say d x squared, right? That would imply the second derivative. But here, the differential is squared. Here, it's x2 is the name of the variable, and you're taking two derivatives. But up here, it is the same, right? So this is always sort of a mess, right? So understand this notation. This is the second partial derivative of psi1, which is a function of all the x's, and it's a mixed partial derivative. But it just so happens, normally it's a mixed partial derivative, right? Because normally you have alpha and beta. But in this case, alpha and beta are degenerate, so we're looking for, so this actually is psi1 x mu dx squared, x2 squared, right? That's how it would be in normal calculus notation. So a bit of a mess, but those are the kinds of things I like to review and get clear. Okay, so now we're working on that second derivative, and so we have to go back to this expression here, and we're taking two derivatives with respect to x2. The first one brings this into a cosine, the second brings it into a minus sign. So we end up with minus x1 sine x2 cosine x3. And that is the first term of this whole mess. Now, what's nice is we can kind of look at this, and although I'm sure I'll screw it up, but this thing doesn't really change. The first term is always going to be x1 with respect to c1, 2, and 3. So now we're after, better write it down, cx1, partial x1, partial c2, partial c2, partial x2, partial x2. And the last one, partial x1, partial c3, partial, there's always a square here. I keep forgetting that square. Partial c3, partial x2, partial x2. So the pattern for this derivative is the same. The only difference is this will end up being an E2 and an E3 respectively. So we'll get E2 over x1 for this second term. And then this guy is this one's second derivative. So this is very similar to this one, except you end up with a sign there. So it's going to be exactly the same, except this will be a sine x3. So x1, and it'll still be an x1, by the way. x1 sine x2 cosine x3. And then the last one will still have, pretty sure it'll still get a minus sign. Yeah, because you're going to end up taking two. So it'll still be psi 3 x1, x1, but now psi 3, two partials of x2 is going to be minus sign back to cosine. So that's where the minus sign comes from, and then you'll have a cosine x2. Okay, so that expression there, gamma 1, 2, 2 equals that thing. So of course we can cancel these x1s and we get minus c1 sine, oops. See, I'm confusing my squares now. Sine x2 cosine x3 minus c2 sine x2, this should be a sine x3. Hold on. So I'm going to change that to make a little red correction. Sine x3, and this is going to be sine x2 sine x3 minus c3 cosine x2, like that. And then now what we're going to do is exploit our relationship for C1, right? We know that C1 is this. It's x1 sine x2 cosine x3. We know C2 is x1 sine x2 sine x3. And we know that C3 is x1 cosine x2. So I think that should simplify things a lot. For example, say we substituted this, x1 sine x2 cosine x3 right here. We'd get an x1 sine squared x2 cosine squared x3. And then here we would get a x1 sine squared x2 sine squared x3. And then here we would get an E3 x1 cosine squared x2. So that should simplify quite a bit. And let's see what it gets us. Okay, I'm going to have to move it to somewhere else. So let's move it here. All right. Let's move it here and try to execute those substitutions. Let's see if I can get this straight. Those substitutions would then look like minus x1 sine squared x2 cosine squared x3 minus x1 sine squared x2 sine squared x3 minus x1 cosine squared x2, which equals minus x1 sine squared x2 times cosine squared x3 minus sine squared x3 minus cosine squared x2. Whoops, these become plus signs, right? Because I pulled out a minus. So this becomes a 1, and then this becomes a 1, which equals minus x1, which in the terms of the regular, which is minus r, right? So gamma 1, 2, 2 equals minus r. And there's the calculation of that one particular Christoffel symbol. Bit of a pain in the butt, but at least we got it. Now we could look at others, right? Do we expect any others to not be 0? How would we think about that to figure out whether others would not be 0 or not? Well, never mind. I mean, I barely got through that one, so going through another one would be crazy. But the point is you can. This is a practical example of how you calculate these connection coefficients, and it can be done for any system as long as you can write down. What do we need to write down? We need to write down. Hold on. You need to be able to write down the actual transition functions, right? Once you have these transition functions, you can calculate these connection coefficients. Now, in this work, it was all flat space, right? So we were dealing with purely a coordinate transformation. That was nothing else than a coordinate transformation. And to understand this in the context of the special relativity that we've been talking about in the beginning, we know that the metric, the flat space-time metric for all of space, is this -1, 1, 1 form. So what is the metric in the new coordinate system? Well, in the new coordinate system, you have to, you know that this interval, this tau interval, this interval of proper time, that's invariant, right? And we know that it equals n alpha beta d c alpha d c beta. And we know that you can convert this by just using the chain rule. It has to be NA alpha d c alpha, oops, dx mu dc beta dx nu dx mu dx nu. And this object here is g alpha beta, which is a function of space-time, dx mu dx nu. So the flat space-time metric gets converted into a different metric using this prescription here. And that prescription should be entirely recognizable to you as the result of a change of basis of the coordinate system. Basically, a change of the coordinate system, and it goes right back to our "What is a tensor" lecture for how the components of a 0-2 tensor transform, right? And that's all it is, right? It's this. You can look at it from this perspective as simply the chain rule. And in fact, in most physics courses, that's all they do to get you there. They say, okay, this is now the definition. Something that transforms that way, this is the definition of a 0-2 rank tensor. But anyway, that is what the metric is. But this is still a flat space-time metric. GAB, the way I've written it, is a flat space-time metric because I've stipulated that in this particular space-time, the entire thing, actually, this should be the way I've been doing the notation. This should be C, right? C sigma, because it's a function of the inertial coordinate system. And this would be a function of the new coordinate system, which is some arbitrary coordinate system. But since I stipulated that there is a coordinate system where the metric is flat and constant everywhere, this is still a flat space-time. It's just expressed in different coordinates. Now, when I relax that assumption, when I say, no, this is only true at a single point, right? Whatever the metric is in this space-time, I can only guarantee you that at a single point, or truly along a single line, a free-falling observer, but at any given point for sure, I can take this coordinate system, I can take whatever coordinate system I'm running in, and whatever that metric is in that coordinate system, I can convert it to a different coordinate system where at that point the metric will look like this. But I can only do it by a point-by-point basis. That's the application of the Einstein equivalence principle to our physics. And that's not a trivial or arbitrary maneuver. That's actually very profound. What I'm basically saying is I'm not dealing with the entire flat space-time of special relativity. I'm not dealing with it where n alpha beta exists everywhere in this inertial coordinate system. But I am saying that there is a coordinate system covering this general relativistic space-time, which would include gravity. There is a coordinate system out here. And there's also a metric associated with that space-time. And that metric is a function of these coordinates, x0, x1, and then presumably there's an x2 and x3. And there is that metric out there. But I can never be sure to be able to take that metric and turn it into the flat metric everywhere. There's no conversion from x mu back to some inertial system, CA, where the metric goes from some value on the space-time at all different values all over the place to 1, 1, 1, 1 everywhere, or minus 1, 1, 1, 1 everywhere. That doesn't exist. That coordinate transformation doesn't exist. But if I go to any single point and I calculate g alpha beta at that single point, say xp, the point p, I'll get some collection of numbers. And there is a coordinate transformation that will take that particular collection of numbers and turn it into this at that point. And once I stipulate that, that is what I'm now saying is that space-time is modeled by a manifold, and that manifold gives me a coordinate system. By definition of what a manifold is, I get a coordinate system. Space-time is somehow the model of our physical reality, and I claim that it's a manifold, so I can give that manifold a metric tensor. I certainly can give that manifold tangent spaces, and in every one of those tangent spaces, there's a vector space at every little location in space-time. Those are the tangent spaces. And I can apply to every one of those tangent spaces an inner product, and therefore I can give a metric to every position in space-time. And the Einstein equivalence principle says, yeah, you can do that, but you better make sure that every one of these points that has a metric, or the metric at the value of the metric at every point in space-time, which is another way of saying the inner product at every single point in space-time for the tangent space at every point in space-time, you better be able to just arbitrarily swap out these coordinates to something so that that metric at any given point is always going to be -1, 1, 1, 1. And that's an application of the Einstein equivalence principle to general relativity. And that's the stipulation that we used. And we used that stipulation to generate that geodesic equation. And by the way, I didn't reference this as the geodesic equation this time, but you see it is. I think I may have actually, because I'm talking about the path in a different coordinate system. But it's not. But the geodesics are the same because in this case, because we're talking about entirely flat space-time back here. In this situation, the geodesics are always going to be straight lines. It's just straight lines expressed in some random coordinate system versus straight lines expressed in the flat space coordinate system, the inertial coordinate system, where they really do look like, where the straight lines themselves, the coordinate system lines themselves are straight. Okay, well that's enough for now. We will continue discussing the connection in the next lecture, where we will talk about it in terms of the covariant derivative, and we're going to start getting into the covariant derivative.